Question 7. Okay, so question 7, I think the tricky part is not in the calculus, it's in solving a trig equation. I'm betting that that's where the issue came from. So on 7, our goal is to find concavity. So any question about concavity or a point of inflection, you need the second derivative. I don't think finding the derivatives was difficult. What's the derivative of cosine? Negative sine. Good. If it starts with a C, you change the sign. Derivative of sine is cosine. Then we take the derivative again because we need the second derivative. Derivative of sine, it stays the same, so it stays negative. Cosine, you change it. So we have the second derivative. Remember, a point of inflection, a possible point of inflection could occur when this is 0 or undefined. But in this case, it's never undefined because it's a sine and cosine function. Those are just smooth waves. And so at this point, we have an equation that has a cosine and a sine. With trig, it's like never good to try to solve with 2 trig functions. So we want to find a way that we can create just 1 instead of 2. So what I'm going to do is I'm going to start by just adding sine over. If I add sine to the other side, I would have negative cosine x equals sine x. What trig function is defined as sine and cosine? What's another trig function besides sine and cosine? Tangent. So let's think about what we know about tangent. How is tangent defined? Sine over cosine. So because tangent is defined as sine over cosine, that's my goal. My goal is to get them to divide by each other so they can have tangent instead of both of the 2 functions. So all I'm going to do, we can do anything you want as long as you do the same thing to both sides. So I'm going to choose to divide both sides by cosine. What's cosine over cosine? 1. So the left-hand side, that's pretty easy. In this case, you have -1. And then on the right-hand side, as we said, sine divided by cosine is tangent. Now it's reasonable if you can get it from 2 trig functions to 1 trig function. Okay, so if we have 1 trig function, so now tangent, I'm thinking, okay, tangent also remember is y over x, because sine goes with y, cosine goes with x. So we're looking for in what 2 quadrants is tangent negative in? Tangent is negative in quadrant 2 and quadrant 4. For what angle does tangent equal 1? 45 degrees or 5/4. If you find that you're struggling with trig, just have your pink reference sheet handy all the time until you memorize it. Like the more you practice it, you're eventually going to memorize it. So if you're doing your homework, I don't want you to just be totally lost because you don't have it memorized. So just keep it handy until you have it memorized. So we know we need a pi-4 angle from here. We're just short of halfway around. So what's the pi-4 from quadrant 2? 3 pi-4, perfect. So one answer is 3 pi-4. Then we need one from quadrant 4. All the way around is 2 pi, or 8 pi over 4. So what's just before that? Perfect. Okay. What are these values that we just found?
Possible.
Perfect. They're possible points of inflection. We don't know if they're a point of inflection. What is a point of inflection? Changes concavity. Good. The point where it changes concavity. So then we do our sine line. Every time you have a sine line, guys, make sure you're always labeling it. So this always needs to be like written out to the side. G double prime or G prime or whatever, because we're going to do both kinds. So always have it labeled out to the side. That's really helpful. Then we list these. Oh, and I guess I don't want arrows because we're not going forever in both directions. We're going from 0 to 2 pi. They typically do that. Otherwise, we'd have like an infinite number of values where tangent equals -1. So we only had to give the values like in 1 unit circle. So it was 3 pi-4 and 7 pi-4. Okay. I don't know what the graph looks like. Sometimes I can rely on graphing, but I don't know what that graph looks like. I can't do that graph in my head. So I'm going to have to rely on like evaluating it numerically. So I needed an angle in between 0 and 3 pi-4. And I'm going to pick the easiest one. Well, imagine 0 and 3 pi-4. What's the easiest angle to evaluate at?
Pi-4.
Pi-4 would be okay, but I'm thinking pi-halves is easier. So I can do pi-halves and I get like 0 or 1. So I'm going to choose pi-halves. So I'm going to evaluate G double prime at pi-halves. G double prime, remember, is this. This gives me negative cosine at pi-halves minus sine at pi-halves. I think of this graphically, so I think of this the cosine wave. What is cosine at pi-halves? 0. Or you could do the point pi-halves is right here, and the point is 0, 1. Cosine goes with x, sine goes with y. So cosine is 0, sine is 1, so we're minusing 1. So we get -1. So that interval is negative. What would be an easy angle in between 3 pi-4ths and 7 pi-4ths? Pi, or 3 pi-half, right? So you can choose anything you want, whatever one comes easier. So I'm going to do pi. This would be negative cosine at pi minus sine at pi. If you want to do unit circle, you could think, okay, here's pi, that point is -1 comma 0. Cosine goes with x, so it's a -1 times the negative. Sine goes with y, so this gives us 1. So that interval is positive. It's a little trickier because 7 pi-4ths is right here, and we need an angle between 7 pi-4ths and 2 pi. What's an angle right in there? Yeah.
Wait, can't you do 2 pi, so it's 2 pi on the interval?
Will it be the same? I guess we could do 2 pi because it's not going to change. I mean, we're stopping at 2 pi, but we know it doesn't equal 0, so we know it keeps going whether it's above or below. So sure, we could do 2 pi, and that would be the easiest. So yeah, let's do 2 pi. So we could do g double prime at 2 pi. So that'd be negative cosine at 2 pi minus sine at 2 pi. What is cosine at 2 pi? 1. So that's a -1. Sine at 2 pi is 0, so we get negative. So now we have our sine line. That sine line pretty much provides us all our answers. When you write this, I think it's really helpful to make the statement that like G is concave up. Because sometimes we just get confused and think we're talking about G double prime, or we're talking about this equation. We're not. We're talking about the original function. We're using the second derivative to give us information about the original function. So G is concave up, I would say, from 3 pi-4ths to 7 pi-4ths. You didn't have to give a reason, but the reason would be because G double prime was positive. So the reason's really short. Okay, then I would say G is concave down. It's concave down from at 0, and this kind of goes to the fact that when we plugged in 2 pi, we got a negative out. If we were to plug in 0, we would get a negative out. So we get to do square brackets on those numbers. In fact, we kind of have to do square brackets. So 0 to 3 pi-4ths and 7 pi-4ths to 2 pi. Because G double prime is negative at those values, whoops, including those endpoints. So in this case, the endpoints should have square brackets. Point of inflection, as long as you state it as a point of inflection when x equals, then I'm okay if you don't list the whole point. So we have a point of inflection when x equals 3 pi-4ths and 7 pi-4ths. What would your reason be if I asked you to give a reason? Those are points of inflection because why?
Changes concavity.
Don't say it. So what changed concavity?
G.
G. So you could say because G changed concavity. On a test, they kind of want you to tell, how do you know it changed concavity? What changed positive to negative? G of x, do you guys agree? G double prime, good. So I would just say because G double prime changed signs. Okay, and that's why it's a point of inflection. All right. Question number 8. I think this one goes a little easier. It's definitely faster anyway, because it's a polynomial. Anytime it's a polynomial, I think it's a lot easier. So we need the second derivative. What's f prime?
15x to the 4th.
Great. Thank you. So then what is the second derivative? That's 60 x cubed minus 60x squared. Would you agree? Okay. When could a point of inflection possibly occur? And this is what? Good. 0 or undefined. Polynomial isn't undefined, so we don't have to worry about it. I would factor out a 60x squared. I'd be left with an x minus 1. This equals 0 when x is 0, and this equals 0 when x is 1. So these are my possible points of inflection. This time I will do it graphically because it's way easier. So I'm going to put 0 and 1 on here. I label it F double prime, and then I come back up and go, okay, well, can I graph F double prime? I think the factored form is the easiest one to work with. What is the degree of F double prime? What's the degree of that polynomial? What was it?
Oh.
3, right? Because we would just count these up. I asked the degree because if it's degree 3, we know it's starting low and ending high. Does it cross or bounce at 0? Bounce, okay? So maybe you guys, we should do a little quick review of this. If it has even multiplicity, that even multiplicity causes it to bounce. So I know it's going to bounce at x equals 0. If it's x minus 1, that happens once, so it's going to cross at 1. So I know it's going to bounce here, it's going to cross here. It has to be like a cubic function, meaning it's starting low and ending high. So it's starting low, it's going to bounce, and then it's going to cross. So if you're comfortable graphing, I think we're less likely to make mistakes graphing if you practice it than plugging in numbers. Really easy to mess up numbers. But what stands out to me is it's below the x-axis, below the x-axis, and above the x-axis. So negative, negative, positive. So I would say F is concave down. Because it's negative on each side, I would just say it's concave down from negative infinity to 1. I don't have to break at 0 because the function was defined at 0. There is one, I don't remember what problem, where you did have to break, but it was because it was an asymptote, like the function wasn't defined at that number. But it's concave down for that whole interval, concave up from 1 to infinity, and then has a point of inflection when what? When x equals what? 1. Why are we not saying there's a point of inflection at 0?
Doesn't change.
Doesn't change sign. So if you get in the habit of always justifying it, then you're going to be good. So it's that x equals 1 because F double prime changed signs. Okay. Let's go to question 10. So the other trig one. They make it look terrible, but I'm hopeful that it's not bad, right? Is it not bad?
Most of the terms can get pulled down.
Yay.
Constants or.
And I feel there's only one trig function at least, so I don't even think it'll be as bad as 7.
Most of the terms get pulled out.
What's the derivative of negative 2 sine?
Negative 2 cosine.
Great. Sine stays the same. The 2 comes down, multiplies by the half, so it just cancels out. So we get negative 1x plus 2. So that's easy enough. The second derivative, well, the derivative of cosine, we change the sign, so it changes to a positive sign. That derivative is negative 1. Oh, yeah, way easier than number 7. Great. This will have a possible point of inflection when this is 0 or undefined. Sine and cosine are never undefined. So we just have this equation. It's easier because there's only one trig function. I would add 1 and divide by 2. Are you guys okay with me jumping to say sine equals a half? And then again, it comes down to unit circle. Does sine go as x or y? Y. So we're thinking what quadrants is y positive? Y is positive in those two. For what angle does sine equal a half? Not pi halves. Pi 6. It's the 30-degree angle. So this would be at pi 6. So quadrant 1 is just pi 6. What's the pi 6 from quadrant 2? 5 pi 6. Good. It's just one short of pi. These are our possible points of inflection. So then you do your second derivative. Again, because it gave us this, we're not putting arrows at the end. We're going 0 to 2 pi. We list pi 6 and 5 pi 6. And you check the intervals. We can do what Isaac said a second ago. We know that it's only changing at these two. So I can use 0 to check to see if it's positive or negative, because it's not going to be 0. So I was thinking, oh, I do not want to pick a number in between 0 and pi 6, because I don't know a number in between 0 and pi 6. I guess I could think of it graphically. Let me show you a couple things. Well, no, I'm not even going to do it graphically. I'm just going to plug in 0. So if I plug in 0 into F double prime, as long as you don't get 0 out, it's good. We just need to know if it's positive or negative. So I'm plugging in 0 into the second derivative. So that's 2 sine of 0 minus 1. What is sine at 0? 0. So we get negative 1. Well, that's less than 0, so it is negative. So that whole interval is negative. The only time you couldn't choose an endpoint, like I can't choose pi 6, because I know if I plug pi 6 in, I'm going to get 0 out. 0 is a positive or negative. But as long as you plug it in and you get a positive or negative, then it's fine. What's the number in between? I like to kind of look here. What's the number in between pi 6 and 5 pi 6? Pi halves, yeah, I always like to choose these ones if I can. So pi halves right here, that's 0, 1. So f double prime at pi halves. I've got 2 sine at pi halves. What is sine at pi halves? 1. So that's 2 minus 1. Well, that's 1. That's greater than 0. Can I use 2 pi? Yeah, as long as you don't get 0 out. So 2 pi, well, 2 pi is exactly the same as 0, right? So I'm not going to bother. I know I'm going to get the same thing out. You guys can finish it from here, right? See where it's concave up, down, points of inflection. Okay, then number 30. Okay, 30. Great. Oh, good. This gives us a chance to practice this speed increasing, decreasing. I think it's only come up a couple of times. You can count on a speed increasing, decreasing question for sure on your next test on the justifying. Okay, so they give us position. They say it's moving along a horizontal line. Often when they say a horizontal line, that's why they'll call it x of t, because it's like the x position as a function of time. When is the velocity of the particle increasing? How do we find velocity?
Take its derivative position.
Perfect. Exactly. Velocity is just defined to be the derivative of position. So velocity would be 3t squared minus 27. In order to know where velocity is increasing,
That's where the second derivative is positive, right?
good, because you would need the slope. When it says something is increasing, that means it has to have a positive slope. You guys agree with that? And slope is the derivative, so it needs to have a positive derivative. So when it says velocity increasing, that is equivalent to saying a positive acceleration. Does that make sense? So if velocity is increasing, it has a positive acceleration. So I'm going to find acceleration. So acceleration would be 6t. I need to figure out where is acceleration positive. I'm going to do a sine line just like I've been doing with the second derivative. So just do it with acceleration. So this equals 0 at t equals 0. Well, when I'm working with time, I'm not working with negative time anyway, so I'm just going 0 to that. So if I plug in any positive value of time, what is acceleration? Positive. Again, always label this. If you draw a little number line right out to the side, so you remember what we're saying is positive. So we're saying acceleration is positive. So if acceleration is positive, that's equivalent to saying velocity is increasing. So it's increasing from, question, can I do a square bracket around 0 or should I do a round bracket? Plug in 0 and see if it makes this true. If I use 0, is acceleration positive? No. If I plug in 0, acceleration is 0. So I should do a round bracket at that 0. Okay, so that's part A. Velocity is increasing from 0 to infinity. Part B asks us where speed is increasing. You're going to have to justify this, and AP only accepts one very specific justification. To justify speed increasing or decreasing, you have to refer to velocity and acceleration. It will be increasing when velocity and acceleration have the same sign. So when will it be decreasing? Opposite signs, right? Okay, well, we already know where, now by same sign, we're talking about positive or negative, right? So not increasing, decreasing. We're talking about where is velocity positive or negative, where is acceleration positive or negative. We have an acceleration sign line. I need a velocity sign line. So I want to do the same thing, but I want to do it with velocity. Well, our velocity equation, was 3t squared minus 27. To create a sine line with velocity, I need to set it equal to 0. I'm going to get 3t squared. I'll add the 27 over. I would divide by 3. What does t equal?
Plus or minus 2.
Plus or minus 3. Do I need to consider the negative time? I don't. Your book, I think, listed it. The AP test won't. Okay, so we're just working with positive time. So when I do my velocity sign chart, I'm going to say 0 to infinity. We're talking about time. And I need to know on which side is velocity positive or negative. So all you do is you pick a number in the interval and you plug it into velocity, or you can do it graphically. I'm going to do it graphically. Tell me what you know about the graph of velocity. What is the shape of 3t squared minus 27? A parabola. Now, I didn't graph this other half, but it is out here at -3, so the parabola would look like that, right? Crossing at -3 and +3. So in between 0 and 3 is velocity positive or negative? Negative, because the graph is below the x-axis. After 3 seconds, velocity is positive. Okay, I'm going to make my sign chart for velocity be up here so that I can kind of compare them. So velocity went negative and then positive. So I have my acceleration number line, my velocity number line. I need to figure out for what values of time they both have the same sign. 3 to infinity. After 3 seconds, velocity is positive and acceleration is positive. So they both have the same sign when t is greater than 3. So velocity, so speed is increasing there. So when t is greater than 3. So that's the answer. Okay. Your justification is just this sentence right here. For some reason, again, on this question is where I get paragraphs as the justification. And I always cringe, and I know right away when I see a paragraph, you're not going to get the point. It's short, and you should show this, but I wouldn't grade that if you're mainly making that statement that they have the same sign. Yeah.
Would it also be when t is greater than -3 and less than 0 because it has a table of a negative sign?
True, and the book probably listed that. I didn't list them because I'm not going to talk about negative time. But you're correct. If you're talking about negative time, that would be true as well. Yep. Okay. So are we good with this assignment? I will save this. I'll do this now before I forget. I'll post this document in case you want to look at it later.
That would C. There was a C.
Oh, there was a C.
There was a C.
Thank you.
Yes, weirdest.
Let's look at C. Okay. So C. What was C? Okay, when is the distance of the particle from the origin increasing? So in order to figure this out, we have to figure out where the particle is. And so you have a number line. Here's the origin. The particle is moving left and right. It depends on its position. Okay, so let's say the position it was somewhere to the right of 0. If it was to the right of 0, it would be having a positive position. If it's moving, what did it want it to be? The distance from the origin to be increasing. Would we want it to be moving to the right or the left? If this was where the particle is. To the right. If we want it to, the distance from the origin to be increasing, so that would have a positive position. So if it was here, I'm going to think of it as a positive position. And if it's moving to the right, what term am I saying? The direction that it's moving. Velocity. Do I want velocity to be positive or negative if I want to move to the right? Positive. So I need velocity to also be positive. I want that to be positive, and I want velocity to be positive. That's when it would be moving to the right. But what if it was over here? If it was on that side, position is negative because it's to the left of the origin. If the particle was on the left side of the origin, and we want the distance between the origin and the point to be increasing, do I want it moving to the right or to the left? To the left. And if it's moving to the left, I would need velocity to be negative. So, say that again. Good, so you can kind of recognize that what's happening is it will be increasing when position and velocity have the same sign. And if they have both positive or both negative. So as long as they have the same sign, then the distance is increasing. So we already have an acceleration and a velocity sign chart. Let's just do a sign chart with position, and then we'll be able to do it as well. So our position function, not so easy. Did you guys, can we solve it on our calculator? Can somebody graph that for us?
It does not look pretty.
Okay. So I only care where the positive time where this equals 0. You guys are probably faster than me. So I'm going to create and graph x cubed. Sorry, I'm not going to switch it over on my computer because it took too long. So I see a negative. I see a positive time. Wait, did it happen more than once? I'm expecting it to start low and end high. Right, if I entered mine in right. Oh, I entered mine in wrong. Yes, yeah. I get something that looks a little bit like that. Does that seem reasonable? If you took the time to graph it. It's a cubic, I could expect it to cross 3 times. So I want to find this point and this point. I am going to show you, I want to show you one thing about storing values. So I'm going to switch this really quick so I can share this. Okay, so I'm going in to my y equals graphing position. This is, I know we haven't had a calculator allowed test yet, and it's going to be a calculator required. These skills are like required that you know how to do this. So always let me know if you have issues with the calculator. I'm going to, in y1, enter in x cubed minus 27x plus 50. Whoops, my window's off for my last one, but that's okay. I wanted to know where it crosses. So it crosses out here, but that's a negative time. I don't care about that one. So the 2 times that I care about are those 2 right there. So when I calculate those, I'm going to do second calc 0. It asks 3 questions, left bound, right bound, guess. If I want to find this first one that's close to 2, you can put it near the 0, but make sure it's to the left of the 0. So I'm to the left of the 0. Oops, mine always goes. Okay, then hit enter, and then go just barely past just the 1 0, not past both. The arrows should point towards each other, and then we'll hit enter. So there's that 0, 2.306. So here's what I would do. I would write, okay, so this happens at approximately 2.036. I want to store that value as A. I don't want to have to write that number again. So I'm going to store it as A. So what you can do on your calculator, you hit second quit. Since right now in my calculator it says x equals, that's what it's defined x to be until I do something different. So when I hit second quit, watch, if I hit X, we can get out of here. Okay, if I hit the X button right next to the green and I hit enter, that's the exact same number I just had. So the calculator just continuously rewrites what it is based on the last thing you did. I want to store this as A. The store button is right above the on key, so I'm going to hit store and then alpha A. So now it's stored as A. I would redo that whole process for the next 0, and then I'm going to store it as B. So I'll show you one more time. So I would go second calc. I want to calculate the 0. So I choose option 2. I go left bound, so left of just 1 0, so just the far right one, and then go just past it. guess doesn't really matter as long as the arrows are pointing towards each other. So that guess, or that 0 is approximately 3.644. Then I hit second quit. I always like to double check that X is still there. So now when I hit X, do you see how the X value is what I most recently did? So then I do store, oops. Then I do store, and then I'm just gonna choose alpha B. Okay, so this store feature, I guess it wasn't like totally necessary on this question, but it is something that is required in this class for some questions. So I have those stored as A and B. I like it because now when I do my position sign chart, so I'll say position sign chart, I'm going 0 to infinity. I can just write A and B. I don't have to write those numbers because I wrote them up higher. I know what they are. I've listed them somewhere. I can use the graph. Notice the graph, it was positive, negative, positive. It was above, below, above, so I don't have to plug anything in. So it was positive, below, positive, or like that. If it has positive position, it's to the right. So we wanted it to have the same. Let's see, A was 2, so A falls about here. And B is just bigger than 3, so B falls about there. So where do position and velocity have the same sign? Where are they both positive? I would say when time is greater than B. If you look at those two, velocity and position are both positive over that interval. Where are they both negative? Between A and 3. I don't know, do you guys believe me? Right? So between A and 3, this one's negative, and A and 3 is somewhere over here, so between A and 3. And that's it. Okay, that one was definitely challenging. Okay, I want to go on. This next thing will be pretty quick. So what we have to cover today is what's called the second derivative test. And students often think what we've been doing is the second derivative test. Up to this point, we've used the second derivative to determine concavity and points of inflection. The actual test that they refer to as the second derivative test, it's to find extrema. So it's to find extrema. What's an extrema? Max or min. I haven't in last night's homework, you didn't find any max or min. We were finding points of inflection and concavity. But we can use the second derivative to help us figure this out. So you would first have to find critical numbers because a critical number is a potential max or min. So you'd want to know what could possibly be a max or min. And then what you're going to do is you're going to use the second derivative to decide if it's a max or min. So if you know it's a critical number, so if the first derivative was 0, let's say it looked like this. At this point right here, the derivative is 0, right? So that point would be a critical number. If the graph is concave down, in fact, I'll do it like this. Where does it? I don't know if it summarizes it great. So I'm going to I'll summarize it here. So if the first derivative is 0 and the second derivative is positive, let's think about what that would mean. So if you have a function, if the second derivative is positive, it's concave up, right? This statement here is saying you've got a graph that's concave up. If the first derivative is 0, you have that. Well, is that point a max or a min? It's a min. Okay. If instead, if I said, okay, well, the first derivative has to be 0 because that's what makes it be a critical number. So if you know it's a critical number, but then you investigate the second derivative, if the second derivative is less than 0, the second derivative is less than 0, is it concave up or concave down? Down. If I have a concave down function, but I have this horizontal tangent, is that point a max or a min? A max. So really, I wouldn't memorize this. It's just consider concavity to decide if it's a max or a min. So I always just kind of sketch a little parabola out to the side to see if it would be a max or a min. Okay, so let's look at this example 7. Oh, one important note. The second derivative test does not always give an answer. If the second derivative is 0, then it's inconclusive. Okay, so it only works if the second derivative is positive or negative. If the second derivative equals 0, then you can't use it and you don't know if it's a max or a min. Okay, because you don't know if it's concave up or down. Okay, second derivative test with the polynomial, so not bad. It wants us to, if you're using the second derivative test, you have to find two things. You have to find critical numbers because we're trying to find a max or a min. So let's find critical numbers. So this would be first derivative. So I'd have negative 12x cubed plus 12x. Critical numbers occur when the first derivative is 0 or undefined. Is that derivative ever undefined? No, it's a polynomial. I would factor out, I'm going to factor out a negative 12x, leaving me with x squared minus 1. This equals 0 at 0 and plus or minus 1. What are these values that I found so far? What do I call these?
Critical number.
Critical numbers. What is a critical number?
Possible.
Exactly, a possible max or min. So we know that these are a possible max and min. Instead of doing the first derivative test, I would typically, in all honesty, do the first derivative test by draw the sine line and decide that way. But to practice second derivative test, I'm going to find the second derivative, and then I'll show you how we get the same thing. So I'm taking the derivative of this. The 3 comes down, so I get negative 36x squared and a plus 12. Okay, so I want to know if 0, 1, and negative 1 are max or mins. So all I have to do is plug them in. So I'm going to do f double prime at 0. I'm checking the critical numbers. Let me add this note. So what I'm doing is I'm going to check the critical numbers to see if f double prime is positive or if f double prime is negative at those values. My first critical number was 0. If I plug in 0, would you get a positive or a negative number? Positive, right? I'll write it out so if you look back, you'll remember where it came from. But yeah, that's positive. If the second derivative is positive, does that mean that the graph is concave up or concave down? Concave up. I'll write it out, but most of the time I'll like sketch a picture, so it's concave up. If it's concave up and the derivative is equal to 0, does that make that x value a max or a min? A min. So we know that there is a min when x equals 0. I would be okay if you say min when x equals 0. What would you have to do if it wanted the point? Plug it into where?
The original.
The original, right? We can do that, but it's time consuming. Okay, let's check the other ones. The other critical number was 1. If we plug 1 in, I'm going to not even write it out. If you were to plug 1 in for x, would this be a positive or a negative value? Negative. So all you have to show is f double prime at 1 is less than 0, which is great, but your notation really, really matters. Make sure you're saying f double prime at 1 is less than 0. Is that concave up or concave down? Down. So if it's concave down, just remind yourself, draw a little picture. If it's concave down and it was 0, then what? What do we conclude? The max. So we have a max when x is 1. Let's do the second derivative at our third critical number, which was negative 1. If we plug negative 1 into here, do we get a positive or a negative? What happens when you square negative 1? You just get 1, right? So squaring it goes away, it's still positive. So negative 36 plus 12, still negative. So I would get the exact same logic here. So that means that there is a max when x equals negative 1. Okay, that is called the second derivative test. So it's how you could use the second derivative to determine max and min. I want to remind you though, we now have 2 methods. Most of the time I would not do this unless it's implicit differentiation. So what you guys have done on a previous section is you did your first derivative test. Let me remind you, first derivative test versus second derivative test. You could have taken your critical numbers and listed your critical numbers 0, negative 1, and 1, and made a sign chart of f prime. If I make a sign chart of f prime, if I were to graph this, what is the degree of that polynomial? 3. But there's a leading coefficient with a negative, so the graph is going to look something like that. It's starting high and ending low. It has 3 distinct zeros, so it has to cross at all of them. So it's going to cross, cross, cross. So the sign chart would be positive, negative, positive, negative. If you're looking at your sign chart, then you can conclude, based on what we call first derivative test, if f prime is positive, the function was increasing. If f prime is negative, the function is decreasing. So if a function changed from increasing to decreasing, is that a max or a min? A max. If it changed from decreasing to increasing, then that's what? A min. And at 1, the max. Notice we are getting the same information that we got using the second derivative test. So there are 2 ways of doing the same thing. So you might say, well, why do we even have this other one? This other one is helpful for implicit differentiation. So you'll see a couple on your homework when the first derivative test does not work. Okay. We just have one last example, example 8. So on example 8, it's kind of, again, they're trying to come up with a way where you have to use the second derivative test and you can't just use the first derivative test. So they do this by giving us a bunch of like numerical values. So it just says g is a function such that g prime at -3. So they're giving us a bunch of stuff, right? G prime at -3, g prime at -1, at 0, and at 2. What do you notice about all 4 of those values though? They all equal 0. If the derivative equals 0, what do we call those numbers? Critical numbers. So I'm going to make a little list so I know I have critical numbers. At x equals -3, I'm going to space them out so I have some space to show some work underneath. X equals -1, x equals 0, and x equals 2. Again, what is a critical number? Possible max or min. So they're giving us now the second derivative at each of these numbers, and then we'll decide if it's a max or a min. So at -3, they're telling us g double prime at -3 is 4. Well, 4 is greater than 0. You have to make that statement. You have to show this comparison. You have to show greater than 0. If it's greater than 0, what else can you conclude? Concave up, good. So you would want to write that down. So it's concave up. I would sketch a little picture. If it's concave up and the derivative is 0, what's our conclusion? It's a min. So I would say it's a min when x equals -3. Okay. Try the next ones on your own. Practice writing that notation. So see if you can make the correct conclusion on these other ones. You guys agree at -1, I got max. What do you think at 0? Inconclusive. 0 isn't positive or negative, so we don't know. So this is inconclusive.
Wouldn't that be where changes compare?
Maybe, maybe not. So it turns out we'd have to know more about the function. So we can't conclude that it is or isn't. Okay, what about on 2? Or on x equals 2? What work do you have to show? Greater than 0, good. So you have to make sure you show that the g double prime at 2 is greater than 0. If the second derivative is greater than 0, what else do we know? Concave up, so we make that statement. If it's concave up and the derivative is 0, what's our conclusion? Good, so it's a min when x equals 2. Okay, so your assignment 3 dash or 3, I forget this one does dashes, my other book does like the dots. Okay, so 3-1b are all of the questions we didn't do. So it starts on 12. 12 says use the second derivative test. So it's 12 through 26. So it's 12 through 26, which would be 15. So it's out.